All right, so picking up where we left off, more or less, talking about how streams flow now. Slightly different topic, I guess. And we had mentioned briefly that meanders, bends in a stream, happen because when you're going around a bend, the water on the outside flows just a little quicker than the water on the inside of the turn. And that might seem kind of weird, but there's actually a lot of precedence for it. Anybody in here was in marching band in high school? All right. Did you guys actually march in formation and stuff like that, do things? Okay. So if you had a long line of people lined up and you guys had to make a turn, what do the people on the way outside have to do compared to the people on the inside in order to keep that nice tight line? Bigger steps. Or I was going to say walk faster, but bigger steps sounds easier. Yeah. All right. So another example, horse racing, or race cars. All right. What track do you want to be on, the inside or the outside? Inside. How's come? It's a shorter track, right? And if you do get the outside and you want to win, you got to go extra faster. Okay. So we see this precedence. The question is why does water do it? Well, again, because water loves to stick together so much. You have to imagine, next time you're at a stream, imagine strings of water molecules flowing by you instead of just this constant rush, because that's really what's going on. All right. So as they go around the corner, those water molecules on the outside are whipped around. Now, we don't get to talk about weathering and erosion here in environmental science class. If I were using this in my earth science class, we probably still wouldn't talk about weathering and erosion. Geology, we definitely would. But you guys have heard those words before, all right? Earth science in high school, perhaps. Weathering is the breaking down of material, right? And erosion is the movement of that broken down material. So the stream both weathers and erodes. So what we see then is increased weathering on the outside of the turn because the water moves faster, it has more energy in it, it's more able to break down that rock. Okay, so that accounts for these meanders getting closer as we move towards the right there, as we move through the slides. The bigger question might be in your mind then, okay, well, why is it staying the same width? All right. Well, that's the erosion part, and more so deposition. We told you that weathering is the breaking down, erosion is the transportation of. All of that is speed dependent. All right. So what happens is when the outside speeds up, the inside actually slows down a little bit. Okay. The other option, she said they had to take bigger steps when they're making a turn in marching band. Well, the other option is that the folks, and maybe they do that was an orchestra, I didn't do marching band, I don't know. The folks on the pivot person might hardly take any steps at all. All right, they have to slow down. And that's what the water does. Okay? And let's just say it's some really weird car race or horse race where they want to keep everybody in a row. That car on the inside has to slow down a lot. Well, when water slows down, it can't carry as much sediment as it had been when it was traveling fast. Remember, speed equals power in this case. So what happens is that sediment gets deposited on the inside. Now, it's not as even as these pictures make it look, all right? But the general idea is that basically that meander moves and keeps more or less the same width. Again, I'm sure it's all, just math, and there's an equation for it. We always say there's no math in geology, but there is. There is. Nature's got a math all of her own, for sure. So, anyhow, this is how meanders form. All right. Now, the big, bold vocabulary word at the top of the page there is about something entirely a different word, but related to meanders, called an oxbow or an oxbow lake. Now, I know we've got a lot of outdated antiquated words in science, but this one, yikes. If they wanted to update it, they'd call it a yolk. Not as an egg sense, but what's another use of the word yolk? Yeah, that's how outdated it is. I know you guys have all seen one. Think about it in another country. Somebody's plowing a field. Yeah. Yeah, the big old wooden horseshoe-looking thing that they put around the oxen's neck. That's what an OXBOW is. Okay? So what we're looking over here is this sort of weirdly U-shaped thing that's called an OXBOW or a yoke. And what happens is a meander will eventually cut itself off. All that going around those bends, that slows down the water a lot. You get a good flow, like a heavy rain, it's quite likely to jump channel there and just flow straight through, and eventually those meanders get cut off. When they do, depending on how much moisture the area gets, go back and think about our various climates. We talked about our various ecosystems. That's going to determine whether or not that stays full or it dries out, within a season. A lot of times you see these swamped in. Now, the thing that gets me is you can really only tell these things from the air, right? So we have something that's obviously quite old based on its name, but you can only see them best from an airplane. So ancient alien astronauts? No, probably not. More like standing on top of a mountain and seeing them. But you'll see a picture here in a moment, I think. I've got the picture in here. Again, these are not my geology slides. It's going to let me change pictures. Yeah, I'm skipping a slide for a minute. But so you can really see them from the air a lot better. And you could probably predict which one might be the next to get cut off. That one may be right up there at the top. Super, super, super close. So what we skipped over here, I will go back momentarily. There's a whole lot of information on one slide. And it's basically just summarizing what I said. But we could use meandering as a way of age dating, if you would, a stream. You can tell if it's a very old stream or a rather young stream. All right, young streams are straight, cutting right through. Old streams wander around, they meander, because they've had much more time to cut through.
Kind of like old people.
Yes, exactly. Except that toddlers don't exactly go in a straight line either. But yeah, I was thinking the same thing myself. I was going to not slander old people. But exactly, it's just like a little old man wandering around. I know I will be, hopefully, God willing. But now, all the streams around here, they're post-glacial. So you're not really going to find anything older than about 10,000, 12,000 years. But believe me, that is more than enough time for meandering to happen. Okay, I'm not going to say a stream lasts this long. That's silly. There's so many variables in that. But what streams we did have here were definitely plowed over when the glaciers came through, and as I implied, they did leave 10 to 12,000 years ago, depending on how far north or south you are. When I was in Ohio, they said 12,000, but New York State were a little higher up latitudinally, so I've been rolling that number back to about 10. But, it varies, and it wasn't an even line either, So, all right, so meandering, oxbows, a little bit about weathering and erosion, and even a little bit about glaciers there. Any questions about that before we move on? Okay. Well, if you think of any. So, just like I'm not going to have you memorize, the average lifespan of a stream, there is no typical flow rate either, okay? I may have said this the other day. I'm not sure why it came up, but you know as well as I do that you could walk 50 yards downstream and it could be completely faster or slower or wider or deeper or shallower than it was where you just left. Streams vary so much, okay? So what I think is a much better idea, instead of memorizing some numbers, is to understand what can make a stream slow down. So when you're standing at one part with your friend and you're looking at it and it's just, trickling along, and you're walking along and you get around the corner and the sucker's, hauling ass. You're wondering, well, what's going on? Why is it doing that? It just changed. How come? So we'll give you those answers instead. So there's 3 things, all right? Now, first one, I'd like to think that if you're walking along and all of a sudden you went down a steep slope and you look back and you see the water's going down that slope super quick, you say, oh, well, yeah, there's a slope here. It's going down, all right? And talking about toddlers a minute ago, this is one of the first things we learn as kids when we get a little toy car, right? It's a lot more fun if you put it on a slope. It'll move itself. So, gradient of the channel, all right? Slope and gradient are not exactly interchangeable. We usually use the term slope when we're going uphill, and we use the term gradient when you're going down. I don't know why, but we seem to. You'll see these signs on the road. A lot of times you see steep grade, right? Trucks use low gear, et cetera, et cetera. But they don't ever say steep slope. So, gradient when you're going down, slope when you're going up. I don't think math has that rule, though. Math calls it slope regardless. So that's an easy one. Shape of the channel is a little more complicated. We've got to show you some pictures to explain that one. And then discharge. Discharge does involve a little bit of math. And I think it's my understanding that you guys did a little bit of this at the stream the other day in environmental science. So we'll get there. So 3 things. So as we said, gradient, increased gradient equals increased velocity, increased speed. Again, speed and velocity, not the same words. Velocity has a direction, speed does not. Okay? Probably only know that if you had a physics class. But we do more or less use them interchangeably. Okay, this is the one that I said that's a bit of a thinker. And even after thinking, you still kind of just got to trust me on this one. So we've got 3 channels here. Originally, we're going to start talking about A and B, okay? The narrow, deep one versus the shallow, wide one. And the question is which one do you think flows faster?
The wide, shallow one.
Wide and shallow? All right. Anybody raise your hands for wide and shallow? Well, let's see. You might not get any people voting against you. Narrow and deep? It's all right. Raise your hand. A couple. I see 2 hands there, maybe. All right. So the answer is narrow and deep. But the reason isn't as simple as you might think. It does, as the bottom bullet here indicate, it boils down to surface area. Now, I haven't taken a piece of string and measured the channel in A and measured the channel in B. If they wanted to be kind and only move one variable on us, which is, nobody likes to do multivariable math, right? They would have kept the same stream size. All right. Regardless, if we're talking about surface area, that means we're talking about friction. And it sure looks like there's more water in contact with the rock in B. And again, even if we want to argue that they were kind and B is really the same area as A, you've got a lot more in water in contact with the air. And believe it or not, you know the word aerodynamic, right? You know, there is a thing such as friction from air. Shallow and wide, generally speaking, moves slower than narrow and deep. Okay? Now, keeping all what I just said in mind, let's look at the top one and the bottom one now. A versus C. Essentially the same channel, but now we threw a bunch of rocks in the bottom. What we've done here in B with those rocks is add surface area. And again, adding surface area means more friction. Can we all agree to that? Friction, surface area connected. Friction slows stuff down. All right, because I'm actually setting up a proof here. Remember those from geometry? Fun times. So if we're agreeing here, and all of you more or less nodded, that the rocks in the way slow things down, what do they call those parts of a river where those silly people in kayaks and sometimes those big inflatable boats go through and risk their lives and have supposedly all kinds of fun?
Rapids.
Rapids. And why is it so fun and dangerous and rapid apparently? What's there? All kind of rocks. All right. So, well, by the end of the PowerPoint, we should be able to answer that. All right. If rocks in the way add surface area, which adds friction, which slows stuff down, then why are rapids rapid? All right. And as I said, we'll get there. So the third thing we mentioned was discharge. Discharge is a wonderful word, isn't it? Especially when you hear it at the doctor's office and whatnot. We're not talking about that here. All right. What we're talking about is flow rate, the amount of water that flows through a given point in a given amount of time. Like, oh, well, that's much nicer than what we were picturing, isn't it? All right. Gallons per minute. You've heard that one a lot. Cubic feet per second is another one. Gentlemen, if you've been staring at a urinal for any time in the last 20-some years, you see this weird little CF integrated. All right? They don't put them on regular toilets usually, so we can't talk to everyone in this case. But they seem to put them on here like you need something to look at. I don't know. But there's a weird little script F. Look for it. And that's cubic feet per second, and it's going to tell you how much water goes through there. But we could picture gallons per minute, cubic feet per second. That's kind of quick stuff. But with gallons per minute, I like to think of milk jugs going down the stream. All right? We could all picture a milk jug, and you could picture a stream full of milk jugs. Kind of like that duck game at the carnival when you were a little kid where everyone's a winner. It's just full of ducks. You can't miss it. All right? So, gallons per minute. Math. I warned you. But it's not hard math. It's easy math. If you can do algebra, you can do this. Now, did you guys see this in lab? Did they have you calculate flow rate or anything for the stream?
They just had a machine where you would check the flow rate on
Yeah, the blue pole with the propeller on it?
Yeah, ours died.
They suck. They're horrible. Did you get what were you in cubic feet per minute or per second? What was it doing? Do you remember anyone? Because it died. You guys all in the same lab?
No.
What were you saying?
Me and her are, some other people are. Polivka. Yeah.
Okay. Well, it would have been in something.
Well, our measurements changed halfway through because the measurements that she gave us later were not.
Measurements of the stream or measurements of the...
The units that were being used.
Oh, okay.
Because of the other two measurements that she gave us to make up for the other two units.
Like gallons per minute units or something? What do you mean?
This is just the speed, right?
Well, we're getting there. That's sort of the point. Were you guys do you have yardsticks out? Were you doing depth and width and stuff? Okay, so you were taking area of the channel. All right, so area of the channel, that's the A there. All right, so that was what the units were switched on? Or the actual speed?
The actual speed.
Okay. So, we did it both ways, and the flow meter was always wrong. I told you maybe the other day we would float balls down there. We'd go 25 yards, 50 yards. There was a start line, a finish line. But I'd always wait till it was warm. And we'd time it. And the ball moves, 50 feet in 10 seconds or something like that. You've got a velocity, right? You've got a speed at any rate. So we're going to use that to get Q. You guys measured the depth. Somewhere along the line, you were going to, I know what you were going to use the flow meter for V. I get it. And you couldn't calculate Q because V was off. All right. So area of the channel. You went along with your meter sticks and you measured the depth. You probably took an average depth for a section. Then you measured the width. You got an average width. You multiplied length times width. You got area, right? It was square foot, more than likely. Velocity, as I said, you could count a number of ways. They've got these things called gauging stations. I don't have a gauging station in here. These little shacks next to the sides of rivers with a propeller and a bobber and whatnot. It tells you how high the water is and how fast it's moving. 24/7, 365, it's always going. And the U.S. Geological Survey is recording all that info. Anywho, so you got your area, some way, shape, or form. You got your velocity. So your area is in square feet. And right now, for argument's sake, we're going to make your velocity in feet per second. When you multiply square feet by feet per second, you jump up to cubic feet per second. Because remember, where are we looking at? Volume is cubic. All right? So you got to get up to the third power there. Let me say it in some more plain terms. The amount of water that can flow past you in 5 minutes is directly related to two things. How big that stream is and how fast that water's flowing. You dig? I mean, it's that simple. I usually give an expressway example. There's a stretch of, I think it's 69 heading out to Rome, where you've got a country road next to the thruway, or maybe you got 69 next to the thruway. I don't know my numbers real well, but you might know where I'm talking about. So you got 2 lanes going 70, all right, on the thruway, and you got 1 lane doing supposed to be 55 next to that one. If you sat there with a timer and had an infinite supply of cars lined up, which one would get more cars through in the same amount of time? 2 lanes at 70 or 1 lane at 55? White hoodie, I know you're paying attention. 2 lanes at 70, all right? Why? Because it's bigger and it's faster, all right? That's all we're saying here, but we're using math to make it all scary sounding. When and if I ask you to do this on a test, some of you can figure it out without numbers. God bless you, that's great. Okay? I'm going to say what happens to V if A goes down, what happens to A if V goes down. If you need numbers to picture it, do something you know makes sense. Q equals VA, 25 equals 5 times 5. Make it a true statement first. 36 equals 6 times 6, something. You follow? I'm never going to give you numbers. I'm just going to say what happens if this goes up and this goes down. So start with something you know. And then if I say, I don't even know if I have a marker here. This is a math class. We actually have chalkboards. Q equals VA, 25 equals 5 times 5. What happens to the velocity of a stream if the area increases? This is where it gets kind of fun and actually applicationable. Smaller. So what did I say? We're going to increase area. And this is where, again, you're not going to get an actual number unless you're really good at math or have a calculator. So we just increased A by 1. And I didn't say anything about Q. So you have to assume it's still 25. Now, we don't know what number that is, but we know that it's a little smaller, 4 something. All right? Has to be. Has to be. We could go the opposite direction. I could say, what happens to the area, and this is where it gets kind of fake because you're not going to increase the stream channel, but what happens to the area if the velocity increases? Again, it's got to go down. But that's where math can be used to prove false stuff, right? This isn't actually how we're going to use it. We're just trying to explain it to you right now, because where this is heading is to flooding. All right? Flooding is nothing more than an increased Q from its normal state. All right? Your stream's at a happy medium, usually has a little extra room to go. All right? But when it keeps raining and raining and raining and snow melting and snow melting and snow melting, that Q goes up. And just like I told you, we can't really get A to change. What's going to happen is it makes its own stream up and outside of the banks.
It's a bit like if you kept dumping water in a bucket and dumping water in the same bucket until it overflows.
Yeah, yes, definitely. Definitely. So I'm going to go through, we talked about this. Don't try to, this is narrative. So the amount of water flowing through a stream at any moment is a function of the speed of that water and the size of the channel. We talked about that. We're going to always keep 2 of the 3 variables straight. Mother Nature, not so dependent on that. She can do whatever kind of math she wants. I kind of like, it's an old movie now, but I've been teaching a long time. I kind of like to think of Matrix time. You guys remember the movie Matrix? And how they just kind of go down into that stop frame motion. All right, you could walk your way through a flood if you take it 1 frame at a time and do the math. It might seem like an instant, but it really isn't an instant. So we talked about this. I used the highway example, though. And again, I'm only going to ask you, all right, to move 1 variable at a time. And I'm never going to give you numbers. So feel free to scribble in your own numbers if you don't remember or haven't figured out how the ratio thing works. As one goes up, the other has to go down. As long as we only change 1 thing at a time. So I used 25 times 5 here. We dropped area down to 3. And we got a jacked up velocity. Now, I know you guys are in the environmental science lab room. You don't really get to play with the sinks too much. And you got those silly little sinks anyhow. But in the rest of the lab rooms, and maybe in high school as well, you had those sinks at the end of the tables, right? And they got those giant 3-inch nipples on the end of them. All right? The reason that's there is to hook a hose up to it, all right? But what's the effect of it? You turn on that faucet and what happens? Everybody gets wet, all right? And if you haven't noticed this, stop into one of the rooms if you see it open. We could take a field trip down to my lab, but I think there's someone in there now. Trust me, you'll turn it on, what seems like a completely normal amount, and it just goes.
That's what happens in the microbiology.
Okay.
Sorry to go to environmental science.
Oh, okay, good. So, and those, but I say that has those tiny little sinks though, right? Or does it have the full size?
The little sinks are on the tables, and then there's
Biggest
two
in the back.
full-size
Okay.
sinks.
All right, good. So you've maybe experienced this. Well, so here's the idea. So that water's been traveling throughout the whole campus, right? In that typical little copper pipe, tubing, whatever it is, 1 inch in diameter, let's say. Flowing along the whole way. And then in the last 3 inches of its journey, it goes from like the size of a Sharpie down to the point of your pencil. In 3 inches. It's Q equals VA. You narrow that diameter a lot and really, really quickly. So is this some huge biology joke, science joke? No. The reason that nipple's actually there is to attach a tube to it so you could run water. And how do you run water? You increase the velocity. That's why. Okay? But it also lets the teachers giggle when everybody accidentally gets wet. It's only like the 4th or 5th time that we laugh at you guys. Because you'd think you'd learn to go a little gentler. But no, I mean, how many times have you operated a faucet, right? You guys know what you're doing. But that's why. That's why. Same thing happens if you increase. Well, I'm sorry, the opposite happens. If you increase the area of a channel, it's going to slow down. So remember we talked about you're walking along the stream with your friend and the water's trucking along just super fine, and you go around the bend, all of a sudden, whoosh, it's just flowing, barely flowing. Look, it should be wider and more than likely shallower. All right? And if you're walking along that and you get to a part and all of a sudden it's a lot faster, check. It should be narrower. All right? Area of the channel is the biggest thing, again, short of a flood, that's going to change that velocity. No, there, I thought I had this in there somewhere. All right, I mentioned to you a little while ago that stream erosion is a function, and stream weathering as well, is a function of velocity. All right? And we didn't exactly, tell you that weathering and erosion are vocabulary words. If you don't know them, please remind yourself, and I'll tell them to you one more time. Weathering is the breaking down of material, just in case they show up on the test somewhere and I don't see them. Weathering is the breaking down of material. Erosion is the transportation of that broken down material. And again, you've heard these words a number of times in life so far. And we usually use them interchangeably, unfortunately. Nobody really cares but geologists, but. All right. So we wanted to get those down because now we're going to modify them a little bit. We're going to talk about competence and capacity. All right. Competence and capacity. These are a function of erosion. These words are used to describe how much sediment a stream can carry. And remember, that's what erosion is, the movement of sediment. Competence talks about the largest size piece of that it can carry. Now, I'm not going to add into all the other crap you guys have to remember. I'm not going to add boulder, cobble, pebble, sand, silt, clay. All right? Again, that's for other classes. You might know sand, silt, and clay already. Did you do soils already in lab? Soil's still coming. All right? So you know those as grain sizes perhaps already. They also look like nouns to you, but in earth science, they are diameters. Sand is 2 millimeters to 1/16 of a millimeter, for example. Silt is 1/16 to 1/256th, and clay is anything smaller than 1/256th. Just, again, you don't need to remember that, but just to give you an idea, we do actually measure this crap, all right? So, which of these is that stream able to carry? Now, on any given day, silt and clay is a given. We've all seen a brown stream, all right, muddy stream. Hopefully that's why it's brown. Silt and clay are carried on a normal basis. Sand, you believe it or not, is kind of iffy, all right? Again, depending on how fast the stream is at any given spot, it may or may not be able to pick up sand. It's so much so that they actually made a special vocabulary word for sand being carried in a stream, if you can believe that. Pebbles, cobbles, boulders, that sucker's got to be trucking, all right? And again, you may have seen a pebble rolling along in a stream, but that should tell you that the stream's moving pretty fast. So competence, how competent is it? What can it lift up? All right, that's competence. Capacity maybe makes a little more sense. What's the total load? What's the total load? How much sand, silt, and clay can it actually carry at any given moment? So competence and capacity. All right? And as I think the next slide is going to tell us, but I'll say just in case, remember these are both functions of velocity. As your velocity increases, your competence goes up. You could carry bigger stuff. As you've been on cold medicine for a couple days too, sorry. As your velocity drops, your competence and your capacity drop as well. So they are directly related. And again, this gets into all kind of stuff when you want to talk about streams making deposits, why you see gravel bars and sand bars. That goes back to Again, when we were talking about the OXBOWs a little while ago, the meandering, okay? This goes to, remember we talked about delta the other day? When the stream enters a non-moving body of water, it drops its load, boom, right here. All right, it's all connected, man, all connected. And there is a flag for it, a slide for it. So again, kind of hovering in the background is that specter of a flood. All right, so we're going to point out here yet again that during periods of heavy flow, streams could move more stuff and bigger stuff. You don't usually see your neighbor's car floating down the stream, right? Usually it can go, fine without it. Now, if your neighbor parks in the stream, that's another story, but you know what I mean. All right, we see these horrible things happening in floods. It's because the stream is way bigger, way more powerful than usual. All right, it's hard to pick the vocab out of here. So you have three big ones. As I hold up 4 fingers. Again, cold medicine. 3 big ones. You've got dissolved load, suspended load, and bed load. Dissolved, suspended, and bed. Dissolved load is just that. It's sediment that's dissolved. But we never really think of that because you're not seeing it. But I think we did a hand raise at some point. Who has hard water? Who has iron deposits in their sink or their toilets? Right? That iron or that calcite was dissolved into the water at some point. We'll call that point A. And it's deposited in your sink or toilet. We'll call that point B. That's erosion. That's transportation. Came out of solution, deposited. So that's what we mean by dissolved load. You don't see this stuff typically, but we know it's there. The water dissolved it out at some point. It's moving along for the journey. Suspended load is the stuff you do see. That's your brown water. All right, there's an age-old trick when we're first trying to teach kids about that. You go, if your class is next to a stream, it only works. And you see this brown water, you got to get a big clear mug of it, you set it on the table for an hour. And all the sediment is going to settle out of it. You get a nice little layer of mud in the bottom and all the clear water. And the little kids are amazed that you did a magic trick. You didn't do a magic trick. You just removed the turbulence, right? The water flowing keeps that stuff floating around in the water column. You remove the turbulence, it all settles out. So that's suspended load. And that's the silts and the clays. And like I said, sometimes sand. And after we get to bed load, we'll talk about sometimes sand. Bed load is just that. You guys told me the other day where the stream bed was, is the bottom of the stream where the rocks are, right? There is some rolling and sliding and banging around down there. Again, that's why most of the rocks that you see in a stream are rounded. It's because they've been in a rock tumbler, if you would, nature's rock tumbler for a very long time. All right. They're not exactly moving, but they're bumping into one another, so on and so forth. And other stuff is banging into them and chipping off the sharp edges. So, dissolved load, suspended load, bed load. 3 main ways. And sometimes sand. There's one word hiding in here. There you go. One word hiding in here, saltation.
If you didn't hear saltation before, you'd think it was putting salt into the river.
It could be. Or removing it, or, unfortunately so many people, not unfortunately, but so many people know desalinization already. But yeah, saltation definitely sounds like salt, and it's got nothing to do with it. But I think one of my wrong answers does say something about salt, so don't choose that one. Saltation is sand bouncing. All right? And what happens is it's that borderline. Okay? The stream's like, oh, I could carry this. oh, no, I can't. And it sets it down. And then, no, I can pick this up. And you get this, and in a cross section, it kind of looks like the sand is just bouncing along. Okay? It's a mixture of suspended and bed load. But it's specific for sand grains and common enough, that they made a vocabulary word for it. All right, and this kind of just summarizes what we've been talking about. Nothing new. All right, so we're going to end this conversation by talking about flooding. It's something that a lot of the areas around here have trouble with. Certainly been in the news, and it may have even affected some of you guys. First 30-some years of my life, I just heard about it. And then one year we did flood, and it really was not fun. So, as we said earlier, flooding, mathematically speaking, is an increase in Q, right? And remember we said we're going to kind of walk through this, right? Let's say you don't mind walking in the rain, so you've been keeping an eye on the stream down at the end of your street. And you know that stream usually flows at a certain rate. So the rains have been coming. You're watching the water get higher and higher. What else is it doing? It's also starting to go faster. All right. What you're doing slowly but surely is increasing Q while keeping A the same. So V is going to go up, and V is going to go up, and V is going to go up. Let me see what slide comes next. Hold on. Let me walk you through a little more, then we'll go to those. So, we know that the water level is going to get higher and higher and higher. We wouldn't call it a flood unless it leaves, right? Otherwise, holy cow, the stream's just really high today. You see how fast it's flowing. You may have had these conversations. You don't say it's flooded, though. When do we say it's flooded? When it goes up and over its banks, right? So, what happens then is that as soon as you go up and over those banks, there's probably no barriers unless you've got some serious geography helping you out here, topography helping you out. It's going to go up and just whoosh over. Which one of those variables just changed dramatically? No. Q's essentially the same as it was a split second ago. Maybe a little more rain, but Q, V, or A. Which one did you change by going up and over the banks? I'm literally doing it with my hands here, folks. What's getting bigger? Area. Yeah, A. Just doubled, tripled in size. And despite those couple extra drops of rain, Q is essentially the same. So what does V do? Plummets. Remember levees? Those deposits on the side of streams we talked about? Boom, you just made some levee material there. But it doesn't matter right now. So that stream keeps flowing and flowing. It's going to hit some sort of natural barrier, be it the curb, be it the slope of your neighbor's lawn, whatever. At some point, it's going to rechannelize. Okay? And if it keeps raining, and then you got to think about upstream. What the heck's the weather upstream? So these things could go on a little longer than it stopped raining where you live, thank goodness. No. All right. So it's going to rechannelize. Q equals VA is going to go through the motions again. And you're going to establish some sort of some sort of new math there. All right, so flooding increases the velocity of a stream, then it increases both the competence and capacity. We talked about this. It equals an increase in erosion. You see all these twigs everywhere. Stream, well, streams do move twigs because they float. They're like boats, right? But you see this one thing, if you walk through, you can see if there's a flood deposit, you'll see a whole bunch of twigs all lined up, kind of interwoven and stuff along the side. Usually there's leaves matted in it as well. That's marking an old flood line. I should take a picture of that next time I see one. So A doesn't stay constant. We said that. The river overtaking its banks is the increase in A. All right, so there's that horrific flood brought down to simple algebra. The problem is the volume of water just, not where it's supposed to be. So, remember I told you we'd end up here. We're in a nice fast river, and we're coming up to a whole bunch of giant rocks in the way. And those Mountain Dew guys, I don't think they have the Mountain Dew guys in the commercials anymore, but you guys remember the Mountain Dew guys? They're always doing crazy stuff. The Red Bull guys, I think they had Red Bull guys too, and gals. So they're like, woohoo, here comes the fun part. And you're going to weave and bob in between all those little rocks, all those big rocks. We've been talking about Q equals VA for a while now. The answer has to be in math. Why are rapids rapid? Despite the fact that we agreed, as we should have, that the rocks add friction, which should, in theory, slow down the water. There's actually a couple possible answers here. They are on a gradient, usually. It's hard to tell sometimes, but there is a bit of a gradient there because it tends to get a little deeper there, too, which, again, goes against what we would think deeper should slow it down. But there's a bit of a gradient, and at the bottom it digs out, so it gets a little deeper there. There is a gradient, so that's one factor, perhaps. What else? What would a word be called for the fact that your kayak might be swinging around in a bunch of different circles and angles and everything like that? So we could use turbulence as well. All right, you got all these rocks, you got the water flowing around the rocks. Might not actually be faster per se, but it's certainly going to jerk you around a corner and so on and so forth. So we've got that going. This wasn't something I had an answer to. This was something that bothered me as I'm setting up this lecture for you guys. I'm like, wait a minute, if this, and this, then why is this? And what I could come up with is basically a mixture of all of those, plus that when you go in between the boulders, you're making a microchannel. You are decreasing the size. Your river is splitting into 2, 3, 4 little channels. So you have a brief moment where your A drops, and that shoots up your V, I think. But you've got the turbulence of the going around the rocks. You've got a bit of a slope. So you got a lot of stuff going on there. All right, so hopefully it was nice to talk about something that's maybe a little more familiar to you guys for a change. You know, we've all seen the woods, we've all seen the forest, and we talk about that, sure. But streams are something that we just, hopefully, at any rate, you're that much more familiar with. Even if you come from a bigger city, okay, there's almost always a river flowing through it, or one in the nearby park, and you go and you spend some time there. Now, The vocabulary words that we added into it, well, that's another story. Always got to be some new stuff, though, some new experiences, right?